Hi guys, welcome back to the final installment of Chapter 5. Chapter 5, we're going to be talking about the tail end here. We're looking at analyzing graphs of polynomial functions. Now we kind of already did this in lesson 5.2 when we were examining an end behavior of these polynomial functions. But today we're going to get a little bit better idea of the kind of the window that you may need to look at for some of these functions to identify some things, some attributes of those graphs. So a couple of the attributes that we want to talk about specifically are two things, and it's what's called local maximum and local minimum. Now, we agree then if we take a look at some polynomial function like a third degree polynomial, maybe it looks something like this. And the maximum of this function is infinity because it goes to infinity, right? But we can identify something called a local maximum, meaning this maximum value is kind of in this region here, it's kind of on top of that hump, as you will. And so we call that a local maximum because it's certainly not the maximum of the function, but within that small region there, that would be the maximum of that function. Now, it wouldn't make any sense to talk about the local minimum in that region because it's not really a relevant point. This point is also a relevant point, and it's kind of at the bottom of a hill, and as you can expect, we would call that a local minimum. We call those points turning points, where basically the function kind of turns and goes the other way. So it kind of comes up from down here, and then it makes a turn at a local maximum, and then it makes another turn at a local minimum, and then it continues on to positive infinity. So that's kind of the gist of this idea of local minimum and local maximum. And so let's take a look at some specific information on some of these solutions. All right, so zeros, factors, solutions, and intercepts. It says let f of x be some polynomial function such that it has n terms. If k is a real number, then the following statements are equivalent. First of all, k is a zero. So if k is some solution to that, where it's some real number, k is a zero of the polynomial function. If k is a zero, then we've talked about this, x minus k then is a factor. All right. We also say that k is a solution to that because, again, if we plug k into this thing, we're going to get that the function is equal to 0. We also know that k is an x-intercept of the graph, and so the point contains the point k0 because the value of k, it would be the x value that turns this function into 0. So effectively what I'm getting at here, and I know that this is getting kind of exhausting, but basically we're just saying, look, how many ways can you say the exact same thing? We can say that k is a 0. We can say that x minus k is a factor. By saying that k is a 0, we're also saying it's a solution and an x-intercept. And so all of those things kind of work hand in hand. And I think they're very, very important ideas that we can address, and so that we're all kind of speaking the same language. All right? So the next piece of this then is we want to take a look at this polynomial function. Now, first of all, it says we're going to use this because it's already factored for us, right? And so we know that this thing has a 0 at -1 and +4. And so we're going to plot -1, 0 and 4, 0. Now, one of the things that we should probably pay attention to here, there's -1, 0 and 1, 2, 3, 4, 0. One of the things that we should pay attention to is the fact that because this is x plus 1 squared, we know that this is then a double root. So we know this is a double 0. And what happens at double zeros? Well, it comes up and it's going to kind of touch there, and then it's going to go away again. All right, it's not going to actually cross through there, just like we had double zeros when we talked about parabolas, right? And then we're also going to have a 0 over here at +4, but it's a single, and so it's going to kind of pass on through it. Now, let me ask you, as we go back and examine end behavior, if I were to expand this polynomial, this would end up giving me an x squared, and then multiply that by another x, so that's going to end up giving me x to the third. Does this function behave like a third degree polynomial in which the leading coefficient is +1/4? Well, again, leading coefficient tells you it's positive, so that means it's going to start down and end up. And again, because it's third degree, that means that it's going to kind of have this type of shape to it. And so I actually kind of want to get down to this part. The end behavior says because f has 3 factors in the form x minus k, we know that it's third degree and it's a cubic with a constant factor of 1/4. We know it's a cubic function, and so it's going to behave in a way that has a positive leading coefficient. So that means as f of x goes to negative infinity. I always have the hardest time writing that. F of x goes to negative infinity as x goes to negative infinity. So essentially, as x goes this way, f of x goes this way. And we kind of already knew that going in. And f of x goes to positive infinity as x goes to positive infinity. Again, as we increase x, the values of the function will increase. So because of that, then, we can kind of use that idea to help us establish an appropriate window. Now, looking at this, they kind of already gave us the appropriate window because we know that the graph's going to fit in this space. But what I want to do is I want to kind of take a few minutes and talk a little bit about how you would use your graphing calculator to get an approximate for this function. So I've already gone ahead and typed in this function, and we wanted to go ahead and take a peek at the graph of that. And there's the graph. And that graph behaves the way that I thought it was going to. It's got a double zero at -1 right here, and it's got a single zero at +4 there. And so since it behaves the way I thought it was going to on the ends of it, that means that I'm seeing enough of that function where I'm pretty certain that somewhere over here, maybe outside of my window, that this thing's not going to turn around and come back down. Okay, if that were the case, then this would have to be an even degree polynomial in order to make that happen. Hopefully you understand why. So I know that I'm seeing enough of the graph, and so now all I have to do is use my table feature. And the table feature tells me that I've got these points that I can plug in. And so when x equals -2, y is equal to -1.5, or -3/2, what have you. When x equals 0, y equals -1. When x equals 1, y equals -3, 2 goes to -4.5, and I'll have to slide over here so you can see some more points. Going back to my chart, when x is 3, y is -4, when x is 5, y is 9. All right, so we've got some points to work with. Obviously, this 5, 9 is off the end of my chart. It's going to be up here somewhere. No big deal. We're not super worried about that. And obviously, again, on the other side of that, this is probably important to take note of. We said that as x continues to the left of things like -2, we had a double zero at -1, right? So here's my double zero right there, and then my x's continue to get negative, or my y's rather, continue to get lower and lower and lower. And as you can see, as x escapes to negative infinity, so do the values of f of x, or the function in this case. So going back over to my chart here then, I'm going to go ahead and start plotting some of these points. So -2, -1.5 is like right in this region here. I know I've got a double zero there at -1. I also know that when x is 0, y is -1, 1, -3, 2, 4.5, that's 2, -4.5, roughly in there somewhere. When x is 3, y is -4, which is in there. Now, we already know I got a 0 there, right? That's the 4, 0 that we got from up here. So when I had to clear the screen, sorry I lost that one. And then when x is 5, y is 9, which, like I said, I guess it's up in here somewhere. All right, so here's the thing. Now we're going to have to try to find a way to make a curve, and we know what the graph of this thing looks like. We know what the graph looks like. We've got a graph right here, and so in order to execute that, we're going to have to kind of come up from here, turn the corner. Now you got to remember that some of this stuff in terms of how we have to instruct this was kind of made with the assumption that you don't have a graphing calculator. So it's hard to imagine coming up with this picture without having seen this first. But again, if you know the end behavior of the function, you know it starts down here, and it's going to kind of continue up here. So the last piece of this basically just says draw the graph so that it passes through the points and has the appropriate end behavior. Okay? So what I want you to do is I want you to go ahead and make a table for the next example, this checkpoint problem here. All right, so we are back at it here. Because this is already in factored form, we know that since this has factors of x minus 2 and x plus 1 and x minus 1, we know that I have zeros at +2. This one gives me a 0 at 2. This one gives me a 0 at -1. And this one gives me a 0 at +1. All right? Now, there are some local minimums and maximums that are going to occur somewhere in here. First of all, because this is third degree, we know that it's going to behave something like, and the fact that the leading coefficient is positive, we know that as x goes this way, my function is going to go this way. And we know as x goes to negative infinity, we know that the function's also going to go to negative infinity. Again, because it's third degree and the leading coefficient is positive, it's going to start down here and it's going to end up here. Now, how does it do that? Again, since all of these are single zeros, again, they're all single zeros because there's no squared terms here. Otherwise, that would make this fourth degree. Now we're just going to say, all right, well, it's third degree, and so it's going to look something like this. Whoops, not quite like that. Maybe something like that, and that's just a guess, so don't pencil that in just yet. How do we get the other points that go around that? Well, then we go ahead and we start to make a table. And so I'm going to make a table over here where I've got a little bit of space that I can see my graphing calculator as well. All right, so we know that when x is equal to, we're going to want -2. I don't have that number. -1, I know it's 0. No idea what y is when x is 0, and then here's 1 and 2, and then maybe let's go to 3. Like I said, past 3 we really don't care much because I know that I'm going to get something that's going to look something like this, and so that's kind of our hope. Let's see what we come up with, okay? All right, so I went ahead and typed this function in. Now I'm going to go ahead and take a peek at the graph and say, does that look kind of like what I expected it to? Absolutely, it does. And so now we use our table feature, and let's see if we can come up with some numbers. Now, we don't need anything past -2. And so if I go back here so I can see, when x equals -2, y equals -24, that's way down here. And so we're not even going to worry about -2, -24, which is way down here somewhere, right? -1, 0, we have when x is 0, y is equal to 4, so 1, 2, 3 right in there somewhere. How about when we know the 1, 0 and the 2, 0, and then when x is 3, y is 16, which is, again, like there's 1, 2, 3, and then 16 is way up in here. So as we said, we're going to have something that kind of comes up, comes through here, turns, and goes back up in that direction there. So there's kind of a general sketch of what we should be looking at. Okay? All right, wonderful. So let's go back to our turning points idea here. And let's talk a little bit about turning points of polynomial functions. Now, we talked about turning points, and let's just draw a general cubic, like a third degree, all right? Maybe let's draw a second degree just for fun. So that's second degree, that's quadratic. This is third degree. Maybe let's draw a fourth degree with a positive leading coefficient. Maybe it looks something like that, all right? In any case, we want to talk a little bit about this idea of turning points. Turning points are places that your graph turns and goes the other way. In other words, they're local maximums or minimums. All right, so the graph of every polynomial function of degree n has at most n minus 1 turning points. Moreover, if a polynomial has n distinct real zeros, then it has exactly n minus 1 turning points. All right? So again, when we're talking about this is an nth degree polynomial, so going back to our third degree polynomial, all right? Our third degree polynomial, again, is going to have at most 2 turning points. So that means it's going to have a local max and a local min, potentially, all right? Our second degree polynomial is going to have at most 2 take away 1, or 1 turning point. While we know a quadratic or a parabola is going to turn one time. What about this fourth degree polynomial over here? Well, it has at most 3 turning points. So it's going to turn there once, twice, 3 times, and then right on back up that direction, okay? Now this last part about having that exactly number of turning points, I want to take a look at maybe a third degree. Sometimes a third degree might kind of come up here and just kind of turn and be flat. Not really exactly flat, but kind of flatten out a little bit. And so that only really actually doesn't have any specific turning points, no local maxes or mins there. But again, it can have at most n minus 1. Doesn't mean it exactly does. But a third degree polynomial that has all, when it says, moreover, if a polynomial function has n distinct real zeros, meaning if it's third degree and it has 3 zeros, then it will have exactly n minus 1. And that's exactly like this example here. Third degree and it has 3 real zeros, that means it has 2 turning points. A fifth degree polynomial, if it has 5 real zeros, that means it had to turn 4 times. All right, so let's make a fifth degree. Here's 1, 2, 3, 4, 5. We say it has to have 5. If it has all 5 zeros, again, for a fifth degree, it means it has to have 4 turning points. So we're going to come up here, we're going to turn, there's 1, there's another turning point 2, then we come up here, and there's a third turning point 3, down here is 4, and then I got to turn and finish up this direction. All right, and so in order to cross through the x-axis 5 times, I'm going to have to have changed directions 1 less than that, or 4 times. All right, so that's just a little bit about this idea of turning points. Now, those turning points, we refer to those as local maximums and minimums. Your graphing calculator has the ability to locate those maximums and minimums. All right, and so what I'm going to do here is we're going to take a look over here at our graphing calculator, and we're going to type in this first function. I'm going to double check, make sure I type that in correctly, and let's take a peek at the graph. All right. Now, in looking at the graph of that, that's a third-degree polynomial, all right? And as we know from the picture, we can kind of see that that's the right end behavior. Again, third degree with a positive leading coefficient. This is positive 1 here, all right? We know that it's going to kind of finish up here and start down here, right? Okay. Now, because of that, then, we then take a look at the picture, and it says, notice that the graph of f of x, or of this function, has 3 intercepts. It has 3 x-intercepts. It means it touches once, twice, and 3 times. So because of that, it has to have changed directions twice. Changed directions once, changed directions twice, and so it has 2 turning points. So we're going to use the calculator's, it says 0 maximum and minimum features to approximate the coordinates of some points. First of all, the x-intercepts of the graph, let's see if we can use that feature on the calculator to come up with those. So under the calculate menu, again, the calculate menu is here. We're going to go second, calculate, and again, you're pressing your trace button, but it's to use the calculate features. We want to calculate some things. We've calculated values in the past. Now we want to calculate some zeros, all right? Because the first thing we want is the x-intercepts. So we want to calculate the x-intercepts. It asks you first, what's the left bound? So we just need to be somewhere to the left of that 0. In this case, we are left of that 0, so we're going to press enter, and now the calculator asks us for the right bound. And so we're going to go somewhere to the right of that 0, which is right in this region. And now it says wager a guess. Okay, let's say our guess is right around in here somewhere. And it tells us that we have 1 0 at negative 1.08613, etc., etc. Now, the calculator is not giving us an exact value. Unfortunately, it doesn't have the ability to do that. And so this could be some irrational solution. I'm not sure what it is, but it's negative 1.086. This is an approximate, and that's just fine. All right? All right. Our next 0 is then going to be calculated the exact same way. So I have to go back over here to my pen, second calculate. We're going to calculate a 0, and we're going to go somewhere to the left of the next 0, which is, we can see the next 0 is right in here. So we're going to press enter on the left of it, go to the right of it, and then wager a guess somewhere around there, and we get back to here, and we have one of the zeros at negative 1.086. The next one is at positive 1.57. We'll call it 1.572, all right? And then the next 0 is somewhere over in this region here, and so let's go ahead and calculate that one. Second, calculate a 0, number 2, and let's go somewhere to the left of it, which, you know, we can be way down here and be to the left of it, and let's go somewhere to the right of it, all right? Now, what you have to be careful of is making sure that there are not 2 zeros in between your left and your right bound. If you set your left bound here and your right bound here, there are 2 different zeros there, and so I'm not sure exactly what you would get, to be quite honest with you. And so our last 0 is at 3.514, and I know that's kind of hard to read, and so let's kind of do this real quick, and now you should be able to see those zeros. All right, and so according to that, we get a 0 at about negative 1.08, 1 at roughly 1.5, and 1 at roughly 3.5. All right. Okay, now we want to identify this local maximum. It sure looks like it's the point 1, 2, 3, 4, 5, 6. It sure looks like it's around 0.6, but I don't know that for sure. But I would say it's pretty close to that point. Let's go ahead and see if we can't find that point. And so we want to calculate a maximum now. So we go to second, calculate, and now you see down below, option number 4 allows us to calculate a maximum. We want to be somewhere to the left of that local max, maybe over in here somewhere. And we want to be somewhere to the right of that, somewhere over in here. And that says wager a guess, and as long as you're in between them, you should be good. All right, now let's take a look here. The value of x is negative 2.5 times 10 to the negative 6th power. Well, negative 2.5 times 10 to the negative 6th power is doggone close to 0. So it looks like I was correct in my original assumption that we do have a maximum value at the point 0.6. We don't have to put negative 2.5 times 10 to the negative 6th power. That's close enough to say 0. All right, so it looks like I have a maximum there at 0.6. And now let's go ahead and calculate our minimum. Same way we calculated the maximum. Second, calculate, but now we're going to use the minimum feature on the calculator, option number 3. Somewhere to the left of that, which is right in here. Somewhere to the right of it, which is over in there. and our guess is it's probably right in there. And it tells us that that minimum is at 2.6 repeating. And we can kind of, it looks like it's pretty close to 2.6 repeating, but then the 9 on the end kind of screws with you. But it's roughly 2.6. So for the local minimum, you're at roughly x is 2.67, we can call it, and y is at roughly negative 3.48.